Welcome to the last applied lecture in the series about finite elements. And today it's about time in the sense that we are going to talk about time discretizations and instationary partial differential equations. This concludes all those topics that we're covering in this course in terms of applications and building your finite elements after having discussed all the ingredients with the grid and the basis functions, the quadrature schemes, then the assembly process, adaptive grid schemes, and then in the end we want to talk about time-dependent problems, because then you can cover a whole huge class of problems. And this is the final ingredient that we're missing. And the outline for today is rather simple. We're going to have a short introduction. What is an instationary partial differential equation and how can we write it down? And then we're going to look into time discretization schemes in general, and then some problems with stability and how to resolve them using implicit methods. So this is pretty standard numerical computation stuff. And in the end, we want to look at how we can use those time discretization schemes on our instationary partial differential equation. So in the sense, put together parts 1 and 2 to generate our extension of FEM to time-dependent problems. And in the end, we will take a look at the relatively famous heat equation and look at some results of how we can apply what we have derived before. So let's start looking into instationary partial differential equations. So let's first do some abstraction. In our stationary case, we had this standard reaction, diffusion, convection equation that you see here. This was kind of the last step we did when assembling our linear system. We had a second order term here, then we had a first order term that was transporting stuff, and then we had a reaction term, and of course on the right hand side this F. So this was kind of the standard example that we can cover with our finite element method implementation. And then now, to make it a bit more abstract and especially to be shorter in writing, we introduce this calligraphic L, a general linear differential operator. And this L applied to a function u does exactly everything that is on the left-hand side of our partial differential equation. So it differentiates u, forms the gradient, and then does the divergence operator and multiplies with b and so on. So this just does all of the things to any function u that is happening on our left-hand side. So this is just abstraction, and we can rewrite the problem to L times or L of u equals f. This is shorter, but nothing has changed, okay? So from up here to down there, we are doing exactly the same thing. We just have a different writing for our PDE. So we have changed nothing yet. It's just to make it a bit shorter. And then we move on to instationary problems. That's the topic for today. So if your solution depends on time, you don't just have u of x, but instead you have u of t and x. So you have a solution at a certain time and somewhere in your domain. So you always, if you look at those time-dependent problems, you always ask about what's happening at a certain point at some precise time. And of course, you also need to add time derivatives, because otherwise, if you prescribe that something is changing over time, but you don't include time derivatives in your PDE, then it won't change over time, right? Then we'll just stay constant over time, and then, nothing happens. So we're introducing those partial derivatives. And then you put this L stuff that we've written down in the slide before together with the time derivative. And now here you see why I have introduced this L, because it makes things a bit shorter, okay? And we can directly say that we have a differential equation that consists of exactly 3 parts. on the right hand side, you still have your external force F that is doing something. Maybe it now depends on time and space and not just on space. Then you have your linear differential operator L that may contain a Laplacian or some convection term, whatever you like. And then you have a time derivative. Okay, so this is just the combination of the two. And of course, if you are talking about something that's time dependent, then this should not just be a differential equation defined in your domain omega, but it is the product of omega and some time interval from 0 to a final time capital T. Okay, this totally makes sense, because if you have two variables, t and x, then they both have to be defined somewhere. Here you see one important thing. Of course, x is already a vector valued quantity because it has the dimension as our space. For example, if we are in 2D, this x actually represents x1 and x2 or x and y, so all those spatial variables. And t is, you could see it as just another variable, but we want to really keep those separated because physically dependence on time and dependence on space are essentially different. And that's why we want to keep this thing separated. We don't just put all those derivatives together, okay? So we always make a difference between t and x. And so this is our problem here. And then to make it a bit more precise, we of course still need boundary conditions just like before. And in the simplest case, we just take our boundary condition as before, this with a function g, might also be just 0. And then we want this to be true for all times. Okay, this is essentially the direct generalization of what we had before. But of course, we can also think of settings where you have u of t and x is equal to some function g that also depends on time. That might be true. We're leaving this out of the picture for now, but this is not much more difficult. But then, of course, because you have another variable, you need an initial condition. Okay, so the boundary conditions are kind of to make things well defined in terms of the spatial variables, but in terms of the temporal variables, the temporal variable t, we also need something to make this well defined, and for that, usually that's something you know from other ordinary differential equations. You need an initial condition. And this, in our setting, reads something like u of time point 0 and any x is equal to some initial function, right? So this u of x is a function that's defined all over omega, and this gives the initial profile, the initial distribution of the quantity inside of our domain. And if you put this all together, you arrive at this system. So while before we had a linear differential operator and boundary conditions, we now have something, a PDE composed of time derivatives and this linear operator in spatial variables, some boundary condition, making sure everything is well defined in terms of spatial variables, and an initial condition to make it well defined in terms of time. And yeah, if you look at this precisely, this is not that much more complicated. So you could say this was the original problem where we started, and the only thing we have added is a time derivative and some initial condition or a boundary condition in time. So what can we do with this? This is a setting now, and I have introduced this general operator L for a reason, to cover a broad class of problems. So what can we do with this? We can model the heat equation. That's the example we will use later on in the rest of the lecture. We can also do reaction diffusion equations, because usually when you consider processes in chemistry or other applications, you're not dealing with a stationary problem. So sometimes when things are not really changing that much over time and you have a flow that is very steady, then you can model it as a stationary process, but usually all of those equations should involve some time dependence. And for that, The standard reaction diffusion equation is just the one that you have been talking about before, but now with an additional time derivative. And the same also for convection and diffusion. This here would be an equation describing a viscous fluid. So yeah, it's not moving too much, it's not turbulent, but it's just flowing steadily. But there are, of course, also things we cannot do with this setting so far. We have just included a single one derivative with respect to time, but of course there exist partial differential equations with higher order time derivatives. For example, the wave equation that is just exactly the same as the heat equation, except for the difference that we now have two time derivatives. And this leads to this oscillatory behavior that wave equations produce. And aside of this, there is also no way of covering nonlinear problems with this setting. For example, here you see part of the Navier-Stokes equation that contains this non-linear convection term where the convection kind of depends on the solution itself. So it's pushing itself forward. That can lead to turbulence. That's why Navier-Stokes is so powerful, but also a bit more complicated. So this cannot be covered in this L of U setting. If you want L to be a linear operator, then this is not possible. So yeah, we have made some assumptions here. We have made some restrictions, but still this covers quite a lot of different problems. And for simplicity, we will now just restrict our considerations to the heat equation, just like in the stationary case where we have always considered Poisson's equation for simplicity. And then in the last assembly processes, we have seen that, well, if you have convection or reaction, everything is essentially almost the same. That's the same thing we're going to do here now. So for simplicity, we will always just talk about heat equation. But then you will see the generalization to reaction, diffusion, convection problems is just the same as before. Flexibility in the choice of L is still given. And of course, you can also include different types of boundary conditions if you want. And we will later on see that this is just done in the finite element part that we already have. So essentially, when you talk about different spatial derivative operators or different boundary conditions, this is just the same as before, so nothing changes there. So after defining our problem setting, of course, it becomes interesting to look at the discretization scheme. So what can you do when you want to deal with time derivatives? And for this, we look at a setting that you probably have seen somewhere in your studies before. So this is the most basic setting that you can imagine. You have something that reads u prime of t is some function f of t and u of t in some interval, and then you have an initial condition. So this is called an ordinary differential equation because it only involves time derivatives. It is an initial problem, an initial value problem, because you have clarified what's happening in the beginning. And this can be vector valued. So if u0 and u of t for all time steps is a vector, then so be it. So you can just talk about an ordinary differential equation in a vector valued space. Okay, for now, this is not clear what this has to do with anything that we are doing here. But let's just focus on this simple problem and do some considerations about time discretization there. Some of this may already be known to most of you or many of you, but still we need the recap to build our groundwork for the rest that we're doing afterwards. And we start with the time grid. Okay, this is in comparison to grids in finite elements where you have to discretize multiple space dimensions and have to think about triangles and rectangles and so on. This is here relatively simple. So you need a time grid on your interval from 0 to t. And what you do is you simply put in some intermediate steps, t0 and so on until tn between 0 and t. And that's that. Okay. So grid in a one-dimensional interval is pretty simple. And the aim of any time discretization method now is to construct a sequence u0 up to un, where this n is just the same as the number of time steps, such that the sequence kind of approximates your exact solution, so that every one of those values here, u0 until un, is an approximation to your exact solution at the corresponding time point. Okay, this is pretty simple, pretty straightforward. If you have some time interval here and you have an exact solution like this and some time grid like this, then, well, if you do some discretization scheme, then you want to have values that are at least close to your exact solution. And then you could do, for example, a linear interpolation scheme and get your exact solution, or your approximated solution. Some remarks. The choice of the time grid can be complicated, or you can make it complicated. So there is a ton of theory about how to properly choose time stepping grids, but we are just going to keep it simple here because we always assume an equidistant division. And for our needs, this is completely fine, but you could always just easily change this for a different scheme. And yeah, there exist countless time discretization methods, and these problems of ordinary differential equations and how to solve them numerically, this is super old, and that's why there is so much theory about it. Firstly, some maybe less familiar approaches. There exist variational methods. The concept is to consider your subintervals, and on each subinterval do an ansatz like a finite element method with ansatz functions and test functions, and yeah, use this to get your approximate solution in each subinterval. There exist parallel time discretization schemes, which is pretty interesting. If you think about the fact that your time is always running linearly, only forward, and you can't revert it. So yeah, it's kind of interesting to think about how it's possible to solve things now and later at the same time on multiple CPU cores. So I've also named some examples here. And then, of course, the simplest idea is time stepping. And time stepping is what we're also going to do here today. We will just try to use derivatives and go from one step to the other. So this covers a huge class, and probably the most famous and simple class. That's what we're going to do here. And the most simple example is the forward Euler scheme. So if you always think about, you're talking about this problem up here. So the derivative of a function is given by some function that depends on the time and the value of the function itself. And yeah, if you have this type of formulation, then you can just say, okay, if I am at some point ui, and of course you start at u0 and go to u1 and then go to u2 and so on. So if you are at a certain point, then you simply take your derivative, which you know from the PDE. So the derivative at a certain point is just f of t and u of t. So you use your derivative, multiply this with a time step, and say, okay, well, I take where I am right now, I take the slope that my ODE is telling me, and my time step is from here to there, so I'm just following this slope, and my next approximation is here. So this is forward Euler. Just take the slope at your current time point and go forward. And we want to apply this for a simple example, just as a recap for you to see how this is done. And this is a very simple ODE that you can see here. U prime of t is just t, and we want to go in 0.5 steps from 0 up until 2. Okay, so these are the times. This is the time grid here that you can see on the right hand side. And let's start. Yeah, okay, of course, u0 is just given by the initial value, so that's just the value 0 that I've extracted here. So my first point is just here. Okay, and then what happens if I want to compute u1? Well, for u1, I have to take u0 plus, and then what's the time difference? The time difference is 0.5. So 0.5 times f of my current time point. So yeah, f of u, f of 0. And f does not depend on u in this case, so that's just 0 plus 1/2 times, and then if I plug 0 into my right hand side, this is again 0, so that's just 0. So my second time point is also here. Then u2, well, u2 now takes u1 plus, again, 1/2, and then f of, my next time point is this one here, so f of 1/2. So that's just 0 plus 1/2 times 1/2, and that's 1/4. So you get your next point here. Then u3 is just given by u2 plus 1/2 times f of, and then number 1. So that's 1/4, no, 1/4 plus 1/2 times 1. And that's, yeah, 3/4, if I'm correctly. So that next step is just here. And then my last one, that's given by u3 plus 1/2 times f of 3/2. And that's just 3/4 plus 1/2 times 3/2. And that's just 3/2. So that last step is here. And then I could do a linear interpolation, and I could just say, okay, well, my solution behavior looks somewhat like this. And if I'm computing the exact solution, which is of course pretty simple in this case, that's 1/2 times t squared, and I compare my numerical solution with the exact one, then you can say, okay, well, this is not perfect, but it's good enough, and it kind of works. Usually, if you take enough time steps, you get this forward Euler method to work, but it requires a high resolution. And yeah, okay, this could be doable for us, but it gets much worse if you have different problems. And to find out about those problems, we look at a different example. Now our differential equation is given slightly different, and most interestingly, the difference now is our right-hand side again depends on the function u itself. That is the most common case, because in the other case that we have just seen, where you just had t on the right-hand side, you don't need any time stepping to compute the solution, right? You can just integrate it, write down the exact solution, and then you're done. But this is much more interesting here. And you have probably also seen methods to get the exact solution for this. So you know that the function that stays itself when you do a derivative is the exponential function. So you just have the exact solution. U star is e to the power of -10 times t. And here on the right hand side, you see that solution printed. You may be wondering why I've chosen such a huge amount of white space around it. Well, the reason for this is if I apply my forward Euler method to this problem, I'm getting this. So what it does is it essentially jumps and oscillates around my exact solution. So I've used the same time grid that I've just used before, 4 steps. But now you see here those values for the solution, they have nothing to do with the exact solution. So it's plain and simple as that. It's not only a roughly good approximation, it's just no approximation at all. It tells you nothing. And that's the huge problem with explicit methods. Explicit in the sense that I only take derivatives at my current time point. These can be very unstable and cause oscillations, which is absolutely unacceptable because it tells us nothing. Because if we don't know the exact solution, then we cannot just identify this to be an oscillation, and we might be left wondering, okay, is this a feature? So does the solution actually look like it? Because, well, you might have cases where a problem has the exact solution to be some type of amplified sine curve, so it might be a good approximation. But in this case, it's just terrible, so we can never use methods and setups that could possibly create a behavior like this, because with this we have no idea if this has anything to do with the exact solution or not. And yeah, what we do want is a stable time discretization. So stable in the sense that if I'm using a coerce time resolution, then I may get a less optimal solution, but it should still have something to do with the exact solution. So it should not oscillate, it should not cause these problems that we have just seen. And for that, we use the so-called implicit methods, and that's the contrast to the explicit one that we have just seen. So instead of, you can guess it, instead of just using derivative information at my current time, I want to include derivative information at the next time point. And for this, an example is the implicit Euler scheme. So if you look at this, scheme here, it's almost exactly the same as before. But now, in contrast to evaluating f, that gives you the derivative, instead of evaluating this at ti and ui, we are now evaluating at ti plus 1 and ui plus 1. So that's the slope of the function at the next time point. Of course, you see immediately why this is problematic. Well, you have on your right-hand side a dependence on the thing that you want to compute. So it's nothing you can just write down. So the simple thing that I just did by saying, okay, I am at u0 and then I go forward like this, that's just not doable. Instead, you end up having a linear or maybe even non-linear system to solve in each time step. So that's a kind of problematic deal. But then if you look at your example again, and you can already guess what's happening here because I've drawn the plot much smaller. If you look at this again and use the implicit Euler method, then you see that it's still, of course, not a perfect approximation, but the numerical solution definitely resembles the behavior of the exact one. So you have stability here, you have a decent approximation. It's not great, but it's decent. So at least you see, okay, it's decaying, it's getting smaller, and so on. The price for this is additional computational effort in order to solve the linear system in each step. But, and here comes an important thing, we later on will be talking about finite elements. And in finite elements, we will have to solve a linear system in each time step anyways. So that's definitely a fact. We need to solve a linear system in each time step. So for us, there is no gain in using the explicit method because we would still have to solve a linear system in each step. So it definitely is the only way to go is to use an implicit time discretization here. And now comes the time to put things together in the sense that we need to figure out how we can use this time discretization scheme for the time-dependent partial differential equation that we have been talking about before. So how can we apply our implicit Euler scheme? So we're not talking about explicit stuff here. How can we apply our implicit Euler scheme to the problem that we have introduced with the time-dependent PDE and the boundary conditions and the initial condition? Firstly, the generalization, the simplification here, we are talking only about the heat equation in the following, so we will make things a bit easier with this. But still the question remains, how can we use the implicit Euler scheme to resolve the time dependence in this problem? Firstly, we need to talk about solution representations. If you remember the stationary setting that we've been talking about the whole semester so far, there we have represented functions, u of x, that are defined on the domain omega by so-called DOF vectors, right? These were vectors that had as many components as you had degrees of freedom in your system. For example, if you have a grid, then this DOF vector was just containing one value for each point of the grid and representing the values of the function at this particular point, in the sense approximating your actual function. In the instationary case, we do the exact same thing. So when we now have a time-dependent solution u of t and x, we still talk about DOF vectors, but now a DOF vector is a vector-valued function, in the sense that at every point in the domain, I now have to specify what is happening there over time. So the format is exactly the same. The only difference is now things are changing over time. And this looks complicated, but if you think about the fact that later on we want to do discretization in time, and then this works much easier because then we're again talking about DOF vectors, except that now we have a DOF vector for each time step and not just one. But this is, later in the end it will boil down to not talking about vector-valued functions, but again, a set of DOF vectors. And this is just, imagine your grid, and you have your points of the grid, and you want to know what's happening there over time. So the component of the DOF vector representing this point here, so that's just u 0, 1, 2, 3, 4. u4 of t is some function telling you what your solution is doing at this particular point over time. Okay, this looks better because we have now kind of found a setting that helps us with a time-dependent solution without changing too much from our original setting. And now we need to talk about assembly, okay? And the assembly is where it becomes interesting because we now use FEM that we have implemented before to replace the derivative, all the derivatives with respect to spatial variables, in the sense that after doing this process that we're doing now, there is nothing in terms of something depends on x anymore. Okay, we want to get rid of everything that depends on x, and this was the same process that we have done in the stationary case also. So you had something like minus Laplacian of u of x is f of x, and that was replaced by s times u equals L, so some constant matrix times a vector is a vector. So you removed everything that had to do with x. Okay, this was the process before. And that's exactly what we're going to do here also. So after the process that we talk about now, we want to get rid of all those x's here. And we start on the right-hand side. So what did we do when we defined the load vector in the stationary problem? Well, we multiplied the right-hand side with a function, so a test function, and we integrated over the domain, and that's exactly what we're doing now too. So formally, you multiply your f with a phi, the basis function, and integrate over the domain, and that gives you a component of your load vector. Of course, if f depends on time, then this load vector component also depends on time. That's why you have an Li of t here now. But the rest stays the same. So you do, at a certain time point, you always have to think about a discretized version already. At a certain time, if I have fixed a certain time, my f is just a function of x, and I can do my standard assembly process, multiply with phi, integrate, and so on. So everything is the same if you keep some constant t, and that's what we're going to do later on. So next step, let's talk about the Laplacian, and for the Laplacian it's also the same thing. So you transform those, you take your weak form and you arrive at this thing here that you have seen just in your stiffness matrix. That's exactly the stiffness matrix of Poisson's equation. And you also have your coefficients u, but of course this is now a time-dependent dot vector, so uj depends on t. But for the rest, this is s times u of t equals L of t. Okay? So this kind of would be the representation of our previous setting. And yeah, let's think about for a second as if this were not a time derivative, but it would just be some function called c. If this was c times u, then we would do our standard assembly process, multiply with the test function, integrate over the domain, and get some contribution to the stiffness matrix. And that's exactly what we're doing now. So let's think about as if this partial derivative with respect to time was just some operator. And then we can form this term here. That's exactly what you would get if you would have your c in here, right? If you had c times u, then this is what you would get. But now we don't have a c here. Instead, we get this part, and we get the time derivative on one of those time-dependent dot vectors. And now, if we call this part here m stands for mass matrix, then we can reformulate this part as m times time derivative of u. But in the assembly process, this is not very complicated. So you always have to keep in mind, in the assembly, this mass matrix is assembled as if it were a reaction term with constant reaction factor 1. Okay, the rest is the same. Boundary conditions are also assembled as usual, so you need to put in some boundary equations in your linear system. That's no problem here. So that just stays the same, and that's why we still have all the flexibility of FEM when we talk about boundary conditions. So let's do a quick recap. We have taken our time-dependent PDE. We have defined a mass matrix, we have defined a stiffness matrix, and we have defined a load vector, just like before. And this is actually just like before. Only difference is now the load depends on t, but that may or may not be the case. And with this, surprisingly, we have gotten rid of all the x's, because we are now integrating over x. So if you integrate over the variable x, you end up with something that definitely does not depend on x. So m doesn't depend on x, s doesn't depend on x, and L doesn't either. So you end up with a system that reads like this: mass matrix times time derivative of u plus stiffness matrix times u equals load vector. And this is the standard scheme that you always have when talking about time-dependent PDEs. Okay, but this is still time-dependent, so we have resolved everything that deals with x, but we still need to do something more. And the next step is we take those boundary conditions from up here and transform them into our setting, because when u is represented by one of those time-dependent dot vectors, we also need to take this function u0 and represent it as a dot vector. And this is now just a standard dot vector, so a constant one. So in the sense, you evaluate your initial function u0 in your grid, and this gives you a representation of the initial function as a dot vector. And this looks quite a lot like one of our ordinary differential equations, because we have a time derivative, and then we have parts depending on u, we have parts just depending on the time, and we have an initial condition. So it's more or less all there. So you see that we use the finite element discretization in terms of spatial variables to transform our initial time-dependent partial differential equation into something that looks quite a lot like an ordinary differential equation with an initial condition. And now let's look at time stepping, because we are almost in a setting where we can apply our time stepping. You see here, it should be like this. Okay, the boundary, the initial condition is already completely fine. And this is almost given. So you see your u prime, that's here. And then you see your f, that's kind of a bit split around. So that's here and there. And there is this m, but the m isn't really disturbing us because that's just a constant factor. So we just take the s times u on the right hand side, and all of a sudden this looks quite good, because now you could write this as f of t and u of t, and you are at in your setting. So this can be used to evaluate your slope at a certain time point and thus create a time stepping scheme. And that's what we're going to do now. So we now take our time derivative and replace it by a classical difference quotient. So just taking the difference between the two function values and dividing over the time step. That's pretty standard. That's also what's done in both the explicit and the implicit Euler method. And yeah, what's left is the part with the right hand side. So of course, let's just do a quick explanation why I say that this happens in both Euler methods. Well, if you have your, let's say, explicit or implicit Euler method, then this reads always something like ui plus 1 is ui plus ti plus 1 minus ti times f of something, depending if it's explicit or implicit. And then if you would subtract ui and then divide by ti plus 1 minus ti, then you would end up exactly where we are. So ui plus 1 minus ui over ti plus 1 minus ti equals f of something. Okay, so what I'm doing here now is I'm replacing my time derivative by this difference quotient here. And this gives me, the first step. And the next step is now to decide what time step to use here and there. So if you would insert ti here, so if you would evaluate your load vector at the current time point and also take the current solution, then you would end up with an explicit method. You would end up with an explicit method because that would mean you would write f of ti and u of ti. And that would give you all of the problems that we know from explicit methods. So you would get terrible stability, and it's just not a good idea to go this way. So we now want to insert ti plus 1 and thus create an implicit scheme. So we replace our time derivative by a difference quotient and we insert ti plus 1 on the right hand side. And here you see why in the actual assembly process it's not a problem if L depends on time. Because in this equation that you're writing down here, you have a fixed time step ti plus 1 in there. So you can just replace your time dependence by some fixed time and then you are golden there. Okay, and now you just do some reformulation. Let's take a look at this for a second. So you, take this stuff on the right hand side. So m times u of ti over ti plus 1 minus ti, that's this one. And you take the s of ti plus 1 up here. And that separates all the things that you know from the things that you don't know. Because in every time step ti, I want to compute my next u of ti plus 1. And I know u of ti because that's my last time step. So this one I can compute, this one I know from the previous time step. This one over here I can compute because it's just a load. So I have some explicitly given function that I can evaluate.
So that part is known, and here I simply have my mass matrix, okay, that's always constant, and there is my stiffness matrix I can also compute. And then this is just like before, a system that we can solve. So think about the original setting when we had minus Laplacian of u equals f in Poisson's equation. We arrived at a linear system of s times u equals L. And if you think about this, the only difference here now is that you have additional time dependence. So you now have m over time step plus s times u equals L minus m times u old over time step. But the general scheme that you have, that you're solving for a dot vector using some assembled linear system and some right-hand side, that stays exactly the same. So we are keeping inside of our setting that we had before, but we have something more. Of course, it's a linear time system in each time step. The mass matrix, as we have seen, is always constant because I've said that m is as if it were a reaction term with constant 1. The stiffness matrix may or may not depend on time. So here it doesn't, because here we just had minus Laplacian of u, but it may be the case that you have different settings where, for example, the diffusivity of the system changes over time. Then you would have something like a general diffusion equation, something like this. And then this coefficient a here could change over time. Then you would arrive at some s of ti plus 1 instead of s. That's doable. And the load vector, in our case, it depends on time, but it can also not depend on time. So it's always a question if your external load is changing or not. And depending on this, you can do a lot of optimizations. So if things don't depend on time, you don't have to reassemble them, but if they do depend on time, you would just compute them again. And now let's look at results. So this is the heat equation in a slightly rescaled version, in the sense that we have our time derivative and we have a factor of 1 over 100 in front of our Laplacian. This is just to ensure that the diffusion happens slowly enough that we are even able to see it with the naked eye. And we're solving this in the in the unit square. So I've used the FEM discretization that we have done before and assembled everything just like explained. The initial condition is this exponential profile. So it's an exponentially decaying profile centered here in the middle of the domain, and then it's going down towards here. So you see kind of a contour plot. This has constant value here in the middle and then going downwards. You can always imagine this to be a plate of metal which you heat just in the middle. So you would just like puncture heat into the middle of the domain, and then you were interested in finding out how this how the heat profile changes over time. So u of t and x will tell you what temperature you have after a certain time has passed at a certain point x in your domain. Okay? And then you see, if you look at this over time, that your temperature is just diffusing towards an almost constant distribution. So over time, for a point out here, for example, you would have an increasing heat because the initial profile would spread in the domain, right? You see, if you take this point x here from the first to the last time step, then you see that it has heated up. If you consider a point here in the middle, then let's call it x2, then you see here the heat has reduced because there you had an initial peak, but it's spreading over the domain. And with this, you can do beautiful simulations of heat. You can do fluid transfers, so in a sense, move this thing around in the domain. So that's a huge class of problems. And that gets us to our take-home messages. even if we restrict our considerations to linear operators, which we have just done, and first-order time derivatives, we model a huge class of problems. Also, those two restrictions can be easily resolved. If you have a nonlinear partial differential equation, you can always try to implement some type of linearization. So approximate your PDE by a similar PDE that is linear. And yeah, instead of just considering first order time derivatives, you can also do second order by applying other schemes instead of Euler schemes here. So these problems are easy to resolve, and all of them follow the same concept. So you will always end up having something like a mass matrix, a stiffness matrix, and a load vector. That is just always the case. Standard methods for time discretization can be applied after assembling the mass, stiffness, and load using our finite element method. So in the sense, we combine our FEM that we have implemented for resolving spatial dependencies, and we combine this with the time discretization methods, some that you probably have also seen before. And this gives us the possibility to solve instationary partial differential equations. I want to note again here, stability is important to ensure good solutions. Otherwise, you cannot be sure if your behavior that you're getting has something to do with your actual solution or if it's just a numerical error. So you should always go for implicit methods, especially because in FEM, that doesn't mean additional effort. It's essentially the same effort. You just rewrite your system slightly differently. And you can optimize assembly depending on the individual problem. So if your, for example, right-hand side function f does not depend on time, you don't assemble the load vector in every time step. If your stiffness matrix does not depend on time, you just assemble this once, which means that you can reduce the process of assembly to the necessary part and only solve a linear system. And because those matrices are still sparse, just like before, you can still use all those efficient linear solvers. And that's it for the implementation part of the finite element method. So we have now discussed all the parts that you need to set up a very basic but still very powerful finite element method. And yeah, I thank you all for your attention throughout this lecture series, and the last two lectures will be about the theoretical aspects of finite elements. So still be with me there, but the software part is now concluded.